So we're going to continue on with Newton's laws of motion, but looking at not only force in two dimensions, but motion in two dimensions as well. Okay, so we're going to continue to build on what we've been learning with free body diagrams, how to break force into components that we can then analyze, but now add the other twist that the motion will be in two dimensions, not just in a single X or Y direction. So our objectives are just that: analyze motion on what we call an inclined plane. So that's a ramp or a slope. And we're going to look at two cases, with and without friction. All right, so here's the example we're going to look at, right? We've got our snowboarder who's gliding down the slope here. How would we apply Newton's laws of motion to analyze his motion, right? And take into account things like friction and the angle at which he's sliding down, his mass, all those sorts of things that we normally consider. Well, the first step is draw the forces on a free body diagram. Okay, now here's what would be acting on him, right? We have gravity, and that's going to be straight down. Even though he's going down a slope, gravity is always to the center of the earth. The normal force, notice, is always perpendicular to the surface. Now, the examples we've used so far, where an object is at rest or in motion in just the horizontal direction, right? The gravity and the normal forces were always in opposite directions. But the normal force will always be perpendicular because it's that snow surface, the hill in this case, right, that's exerting the force on the snowboarder. And the gravity will be straight down. We might have friction, right, that will always be in the opposite direction of motion. So those are the three forces that we have. Now, as we put our free body diagram together, we kind of have a choice, right? Notice we've got forces in the X and Y direction. So if we were to draw those into our free body diagram, some of these we're going to have to resolve into their horizontal and vertical components. Now, here's where we have a choice, right? Which way are we going to set up our coordinate system so that we can make this problem as easy as possible, especially when it comes to resolving these forces into their horizontal and vertical components. So what I'm going to suggest is that we use a system here where the x-axis is the same as the slope or the inclined plane. And the y-axis is the direction that is perpendicular to the plane. And what that does is it puts our frictional force and our normal force already in either the x direction or the y direction. And so it just leaves us with the gravitational force that we need to resolve into its horizontal and vertical components. So we need to know the angle to do that, right? So the angle of the slope would be the angle between the gravitational force here and it turns out to be the y-axis. So let's resolve these into their components. We're going to have a y component, right? That'll be in opposite direction of the normal force. And we're going to have a x component that will be in the direction of motion down the slope and opposite of friction. So if we bring that to form our right triangle, we can now use our trig identities, right, to find the forces here that would be in the x and the y component. So here it is, right? We did a bunch of this in the last lesson. So gravitational force times the cosine of the angle will give us the y component. And the gravitational force times the sine will give us the x component. Now, these are a little different than the problems we did last week, and that's because, right, we've changed our reference, our XY coordinate system reference to match the normal and frictional forces. Okay. All right. So So these are going to be two equations we're going to use over and over again on these kind of problems to resolve the gravitational force into their components. And once we do that, right, then we have a free body diagram that we can analyze and find things like the net force and the acceleration. So let's apply that to a case where we have some actual numbers. We have a 62 kilogram snowboarder, and he's going down, in this case, a frictionless slope at 37 degrees. And we want to find all the components and then eventually find the acceleration down the slope. So let's put our free body diagram together. Notice how I'm orienting the X and Y coordinate system. Gravity is straight down, normal force is up. We have no friction, right? So we don't need that going up the slope. So now we just need to resolve the gravitational force into its two components. Okay, so let's do that. If we put in the mass of the snowboarder, his acceleration due to gravity, and cosine of 37 degrees, we see that the y component of the gravitational force is 495 newtons. Let's do the same now for the x component, the component that's going to cause him to accelerate down the hill. So we have 62 times 10 again, this time the sine of 37 degrees, and we get 373 newtons. Okay, so that x component of the gravitational force is the net force that's going to cause him to accelerate down the hill. So we can calculate that acceleration, put in 373, divide by his mass of 62 kilograms, and we get an acceleration of 6 meters per second squared. Now, this number should always be less than 10, right? Because we're not in free fall, but think about it, the steeper the slope is, the greater the acceleration, or the flatter the slope is, the lower the acceleration. So this is a good check of your math. If you come up with an acceleration that's 12 or 14 meters per second squared, something went wrong along the way. All right, let's try another one. And this time we're going to add in friction. So the same mass, same angle, but the coefficient of friction is 0.15. Okay. So again, let's do our free body diagram. This time we do have frictional force, so we'll show that going up the hill. And we're going to resolve that into its horizontal and vertical forces for gravity. So we did this already, right? Now we want to write an equation for the direction of motion, the x direction of the x axis, positive x direction. So think about this. What we really want to do is find the net force, right? So the net force in the direction of motion is going to be the component of gravity, right? That is in the x direction minus the frictional force that's going back up the hill. Now, what is the x component of gravity? Well, that's what we can put into our equation here. So notice the gravitational force is just equal to mass times gravity. The net force from Newton's second law is equal to mass times acceleration. And then we still have our frictional force that's calculated by taking the normal force and multiplying it by the coefficient of friction. Now notice, I'm going to stay with our variables here until the very end before we put in some numbers on this. So what do we know about the normal force? Well, the normal force is the y component of the gravitational force, right? So if we take this and put it in for our normal force, we now have this equation, right? The mass times the acceleration of the skier is equal to the component in the x direction minus the coefficient of friction times the component of the gravitational force in the y direction, sine of angle and the cosine of angle. So what are we trying to solve for here? We're trying to solve for the acceleration, right? But notice we have mass in every one of these terms. So the mass drops out. It turns out we don't need to know the mass to calculate the acceleration. And what are we left with? Well, we have acceleration equals, and I'm going to factor out a g. Acceleration due to gravity shows up in both terms. So I'm going to factor that out using distributive property here. And what do we have left? The sine of the angle minus the coefficient of friction times the cosine of the angle. Okay, so we've derived kind of an equation for an object going down a ramped incline, a slope with friction. And it gives us the acceleration down the slope. Now, we could also use this, right, for acceleration without friction. If we put in 0 for the coefficient of friction, it just becomes gravitational force times the sine of the angle, and gets us back to that component down the slope. All right, let's put in some numbers here. I guess I'm using 9.8, and we get 4.7 meters per second squared. So you notice a little bit less than the previous problem. We had 6 meters per second squared, but now that we add friction in, it's a little bit less. Okay, so remember that formula. It can be handy, but you should also be able to either derive it again or to just start from scratch and solve problems here using our normal sets of equations and our free body diagram analysis. So let's have a little fun with this, right? If we have 3 snowboarders that are going to race down the hill, they're going to go down 3 different tracks that have different angles, different coefficient of frictions, and different lengths, and to see if we can figure out who would win. So for each track, we want to find the acceleration, the time, and the final velocity. Okay. So I'm going to leave this for you to work. We can do this together in class as well, right? But the first step certainly would be to find the acceleration for each, and then knowing the length that they need to travel, that's our distance, right? Calculate the time, and then we can also figure out what their final velocity, what point are they going to accelerate to when they reach the finish line. All right, here we go. Anybody know who's going to make it first to the finish line? Let's see. All right, so if you had skier B who got across the finish line with the shortest amount of time, you are correct. Right. So here's what the actual values is. Again, I'm not going to go through the detailed steps here for each one. I'll leave that to you, and we can work on some of these in class as well, right? But we see that skier B had the shortest time of 8 seconds. He didn't necessarily have the highest acceleration, but he did have the shortest time. He didn't even have the maximum velocity. It probably helped a little bit, right, that he had the shortest distance, 116 meters to go. All right. That's it for this lesson. So we should be able to set up our free body diagram to be able to analyze the motion on an inclined plane with and without friction. The key is, how do we set up our X and Y coordinate system so that all we have to do in resolving these forces is apply it to the gravitational force. All right, that's it for today. There's an assignment that goes with this.